Okay, it is about time for us to move on to our next section, section 1.2, which is looking at time. So let's take a look. So times will follow the same unit conversion process that we saw with lengths, where they're algebraic quantities that can cancel out. That's very convenient. Standards of time in the past have included, encourage you to think for a moment if you have any ideas of what standards might have been. Let's take a look. One is the rotation of the Earth, right? The Earth rotates, that's 24 hours, that's 1 day. Boom, there's a standard. Well, to get more precise, we could use quartz vibrations, that's what's often in watches, or atomic clocks with time signals sent out by radio so others can calibrate their clocks. So the official definition is now that 1 second is the time taken by some crazy number of oscillations of the light of a specified wavelength emitted by a cesium-133 atom. So there you have it. That's our most precise form of measuring time for the moment. And the variation in the length of day as measured by some atomic clock, as our standard is as shown, where this is over the year, the difference between the length of day and exactly 24 hours in milliseconds. So the vertical scale is only 3 milliseconds, right? That these are about 2 or 3 milliseconds. That's telling you how far off a day is, like using the rotation of the Earth versus using an atomic clock. In other words, atomic clocks are highly precise, and Earth's rotation is relatively imprecise, where it's very, very slightly affected by tides, by winds. They can very slightly change its rotation, and it's something that can actually be measured. Is it a lot? No, but it's something that if you care about a super precise measurement of time, then you'll be inclined to focus in on that, which is why we have a more precise standard of the atomic clock at this point. Now, continuing right along, section 1.3 takes a look at mass, which is our other base quantity in addition to length and time. So for mass, we have the standard kilogram that defines mass base quantity. And it's a cylinder of platinum and iridium stored in France. Accurate copies of this cylinder have been sent around the world, and other masses can be measured by comparing them against these copies. So this is why mass is defined by a kilogram and not a gram, because a gram would be very, very tiny, and it'd be hard to keep it precisely 1 gram, versus a kilogram is a nice chunk of metal, as you can see in this picture here. It's under these 2 glass jars to be under vacuum to try and reduce any effects of atmosphere, but it still isn't the most convenient to have this chunk of metal. It's not totally pure. And so it turns out this is the one thing that is incorrect in your textbook, to my knowledge. If you find other things, please let me know. And that's their standard kilogram is no longer a cylinder. Standard kilogram instead is defined by a constant of nature known as Planck's constant. So this is a universal constant. Instead of a physical object, it's something that is truly accessible by all. You don't need to pay for some expensive copy to be sent around and compare to that copy. So there are very fancy machinery that can be used to determine this, to make that measurement. And so if you want to read more about it, there's a really nice article on this. This is known as a kibble. So that's a cool side note, tidbit. This isn't something you'll be required to know because it's not in the textbook, but I had to highlight it because this was as of a couple of years ago. Very recent news, very exciting in the nerdy science world. All right, so going back to our textbook, more familiar, another standard for mass is the atomic mass unit. This one's often used in chemistry when you're dealing the very, very small scale. The atomic mass unit is in units of U, and it's based upon the fact that 1 atom of carbon-12 is assigned a mass of 12 U. So that's the base quantity, the definition of it. We assign the atomic mass unit based upon carbon-12. So this is used for measuring masses of atoms and molecules, very small things, and you can convert between the atomic mass unit and kilograms with this factor of 10 to the minus 27, right? This is it's a tiny, tiny fraction of a kilogram. And interestingly, this is known plus or minus 10 times 10 to the negative 35 kilograms. So this is showing the uncertainty in this conversion factor, that it's known to very good precision, which is quite impressive. Finally, masses are going to follow the same conversion process as lengths and time, so we can treat them as algebraic quantities and cancel them out, which is great. All right, now when we talk about mass, another quantity that we'll often care about is something known as mass density, or it's often referred to as just density. It's the mass per unit volume. And so we can write density for the symbol that's used is the Greek letter rho. I know it looks like a P, but it is not a P. So when I write it, I try to make it extra curvy just to highlight it, that this is the Greek letter rho, because our book will also have a lowercase p, right? And so I'll try and make that clear that it is different than rho. We'll also have a capital P. So it's another example of there just are not enough letters in the English language. I'm sorry for that. But you can note that this is rho, slightly different than P. All right, so if you want to calculate the density of a material, then if you know the mass and the volume, you can just divide those out. And it also shows you the units of density, which are neither that of purely mass or purely volume. They are mass divided by volume, kilograms per meter cubed. So there we have our density units in SI form, right? Kilogram is the SI unit for mass, cubic meters, SI unit for volume. If we want to find the mass of an object and we know the density and volume, then we can just multiply the volume across to both sides, and the volume would cancel on the right, and so we have mass is equal to density times volume. So we can calculate that out as well. And finally, we could look at an example where you find out a truck's battery acid with 1280 kilograms per meters cubed is 250 kilograms. What is the volume of the battery acid, right? Well, first off, we note that it gives us density. We have a clue based upon the unit, but they also even show us the symbol for density. So that's really cool. Then we have this 250 kilograms. We have to figure out what that is. And it doesn't give us the words to describe that quantity. So that's where the units are a very good clue. We go kilograms. What units, what quantity goes with kilograms? Ah, that's mass, right? And so this is a really good way to think about it, to go, okay, mass is 250 kilograms. Because once you identify the mass and the M and the rho, then you go, hey, we want to find the volume. And I have an equation that has density, mass, and volume, right? I already know that density is equal to mass divided by volume. So if I want to find the volume, I can just switch it out with the density there, right? I can multiply the volume up, divide by density, and I have that volume is just mass divided by my density. Sorry for the messy writing there. But sure enough, we can calculate the volume with mass divided by density, and we have kilograms divided by kilograms per meter cubed. So the kilograms will cancel, and then we'll have units of 1 divided by inverse cubic meters. And so that comes out to cubic meters, which is the units that we would expect for volumes. That shows us that we did the calculation properly. We are very happy. There is much rejoicing. So that pulls us through an introduction to length, time, and mass, and how we go about measuring them.